Last time, SIDH used two secret isogenies and a carefully chosen package of torsion-point images. Those auxiliary points let Alice and Bob transport each other's secret subgroup and arrive at the same final J invariant. For years, the protocol's security rested on the belief that these evaluations revealed useful information, but not enough to reconstruct the hidden isogeny. The important point is simple. The secret isogeny itself stayed hidden, but its action on an entire torsion basis was published. Episode 5 is the story of why that distinction collapsed. On July 30th, 2022, Wouter, Castryck, and Thomas Decru posted a paper titled, "An Efficient Key Recovery Attack on SIDH." It was not a small parameter improvement, and it was not a quantum attack. It was a practical classical key recovery attack that destroyed the central security assumption behind SIDH and SIKE. The original Castryck-Decru attack used a special higher-dimensional construction and the known structure of the SIDH starting curve. Within days, related work clarified and generalized the picture, culminating in Damian Roberts' polynomial time framework. This episode focuses on the common mathematical idea behind those developments. We need one new tool, the dual isogeny. If phi maps E1 to E2, its dual phi hat travels back from E2 to E1. Following phi by its dual is exactly multiplication by the degree of phi. So if the secret isogeny has degree d, phi hat composed with phi is bracket d. The same identity holds in the other direction. Dual isogenies are not needed to run SIDH, but they are exactly what lets us package the secret map into a larger, highly structured matrix. A useful intuition is interpolation. With an ordinary polynomial, enough evaluations can determine the whole polynomial. SIDH publishes the secret isogeny's values on a torsion basis, so it is natural to ask whether those evaluations can determine the hidden map. But we should be precise. The attack is not literally Lagrange interpolation. Instead, it embeds the secret isogeny inside a higher dimensional isogeny. The public evaluations reveal the kernel of that larger map, and the kernel lets us reconstruct it. The interpolation analogy captures the surprise. A few structured evaluations contain far more global information than expected. The attack leaves the world of single elliptic curves and moves into higher dimensional abelian varieties. An elliptic curve is a one-dimensional geometric object that is also a group. An abelian surface is the two-dimensional version. The simplest example is a product E1 times E2. Products of 3, 4, or more elliptic curves give higher dimensional abelian varieties. Why go up in dimension? Because extra coordinates create flexibility. We can place the unknown secret isogeny beside scalar multiplications and dual maps, arranging them into a matrix with a kernel that the public SIDH data reveals. A homomorphism between two products of elliptic curves can be written as a matrix. The first output coordinate combines a map from E1 to F1 with a map from E2 to F1. The second coordinate does the same for F2. If we place the input points into a column vector P, the entire map is simply a times P. The dual of a matrix map is obtained by transposing the matrix and replacing every entry by its dual isogeny. We call an n-isogeny when a dagger times a equals multiplication by n on each source coordinate. The intuitive version is that it behaves like a square root of multiplication by n. In dimension 2, an n-isogeny has degree n squared, so its kernel has n squared points. Start with a secret isogeny phi from E1 to E2 of degree 3 to the m. Call that degree d. For the cleanest version of the construction, suppose 2 to the n minus 3 to the m is a perfect square, a squared. Equivalently, a squared plus d equals n, where n is 2 to the n. Now build this 2 by 2 matrix map psi. It combines scalar multiplication by the secret isogeny phi and its dual. The unknown map has become one entry of a larger endomorphism of the product E1 times E2. If we can evaluate psi, then extracting phi is immediate. Feed psi the point p, 0. The first output is a times p, while the second output is phi of p. Project onto the second coordinate, and the secret isogeny is sitting right there. So the whole attack reduces to one question: can the public SIDH data reconstruct psi? Now multiply psi dagger by psi. The off-diagonal terms cancel. On the diagonal, dual phi composed with phi contributes multiplication by d, and the scalar terms contribute a squared. Since a squared plus d equals 2 to the n, the product is bracket 2 to the n times the identity. Therefore, psi is a 2 to the n isogeny on the abelian surface, E1 times E2. Kani's lemma gives an explicit description of the kernel. For every 2 to the n torsion point P on E1, take the pair 3 to the m times P in the first coordinate and a times phi of P in the second coordinate. The collection of all those pairs is exactly the kernel of psi. And this formula is the turning point. The hidden map phi appears only through its values on 2 to the n torsion, the exact values SIDH publishes. SIDH gives a basis PA, QA of the 2 to the n torsion, together with phi of PA and phi of QA. Because phi is a group homomorphism, those two images determine phi of every torsion point. In particular, they give two generators K1 and K2 for the entire kernel of psi. The auxiliary information was supposed to be harmless help for the honest parties. Instead, it reveals a complete higher-dimensional kernel. Once the kernel is known, algorithms for isogenies of abelian varieties reconstruct psi. This is the higher-dimensional version of the kernel determines the isogeny principle from episode 2. Strictly speaking, we are no longer using Velu's original formulas for elliptic curves. We use their higher-dimensional analog, implemented with tools such as theta coordinates. Then evaluating psi on p, 0, and projecting to the second coordinate recovers phi. In the square case, SIDH is broken. Of course, 2 to the n minus 3 to the m will almost never be a perfect square. Damian-Roberts framework gains flexibility by replacing the scalar A with a 2x2 endomorphism alpha. Whenever the difference is a sum of two squares, alpha dagger alpha equals multiplication by that difference. The same Kani construction then lives on a product of four elliptic curves. The matrix is larger, but the logic is unchanged. Public torsion images reveal the kernel of a higher dimensional map that contains phi as one of its entries. To remove every arithmetic restriction, use Lagrange's four-square theorem. Every positive integer is a sum of four squares. Fermat anticipated the statement, but Lagrange gave the proof. Four squares let us construct the required endomorphism on a product of four copies of the starting curve, and Kani's construction doubles the ambient dimension to 8. The final matrix is an unpleasant 8x8 object, but conceptually nothing new happens. The secret isogeny is embedded as a matrix entry. The public torsion images determine the larger kernel, and reconstructing the larger map reveals the secret. This gives a general polynomial time key recovery strategy. And there we have it, SIDH is broken. But the distinction at the end is crucial. The attack does not solve the generic supersingular isogeny problem. It does not make arbitrary paths through the isogeny graph easy to find. It exploits the extra torsion point information that SIDH deliberately publishes. SIDH failed because its public key transformed a hard path problem into a reconstructible higher-dimensional kernel problem. The isogeny problem survived. The protocol did not. For the rest of the series, we will build toward protocols that do not publish SIDH-style torsion information, and that can even turn higher-dimensional isogeny techniques into useful machinery. But to get there, we must temporarily leave the geometric picture and enter the frightening world of algebra. Next time, quaternion algebras. Thanks for watching.